Stop that. Thank you. I want to show you something real quick. So as I am certain you are all well aware, we are currently scheduled to have a quiz on Wednesday. I'm going to move that to be Monday. So we're going to change that to the 21st because we're going to finish up chapter 3 today, and I don't like giving a quiz the next day after we just finished talking about something. You guys understand? Okay.
Yes.
Ooh, I like it. I like it. And on the note of quizzes, so as people come in, I'm going to have to say this again. Maybe I should do this so I can just... You can do it, Jeff. You can do it, buddy. Let's see, right here. So I'm going to change this to... Oh, I'm doing the mouse again. Oh, crap. All right. Hey, look at this, people. Hey, people. We're going to change the quiz on probability. We're going to change it to be Monday the 21st, so a week from today. It's my birthday. It'll be my birthday gift to you guys. Aw, Jeff, you really, really didn't have to do that. Okay. So we're going to finish up chapter 3 today. I've got a worksheet that I'm going to try desperately to get you guys to collaborate on, to work on. And there's even a practice quiz that I'll have an answer for on Wednesday. So more people just checked in. The quiz will now be on next Monday, the one that was scheduled for this Wednesday. It will now be moved to Monday so that we have time to go over the whole thing. Okay. Did you guys all get your quiz 2?
Yes.
Yes.
Yes, okay. So I am learning. So I have determined that it worked decently well. There were still some technical issues. So what I'm going to do is next time I'm going to do it the same way, but I'm going to have you turn it in. Like I'm going to create a place to turn it in like a normal assignment. Because the submission thing with the quiz was kind of weird for you guys, and it definitely sucked for me. Not that you have to know this, but I had to go to each person, individually download their quiz, grade it, and then individually send it to you when it was done. And that, I'm not going to do that again. That was crap. That was terrible. It took me 2.5 days to finish that whole process. Anyway, so the quiz will be Monday, and it will work basically the same way the last quiz did, except you'll have an easier place to submit your quiz when you're done. Is everybody with me on that? Okay, all right.
Yes.
Let me see. So I want to show you right now what I have added. So if you go to the modules and there's the quiz module, you'll now see quiz 2 corrections. So you can turn in your quiz 2 corrections right there. So you should have gotten my an email from me on Canvas with your quiz attached. So now you can make corrections and submit it right here. Cool, I like it. And you should be able to see your grade into your grades in quiz 2. You should be able to see your grade up in there. Somebody pointed out to me that I forgot to put them in there. I was like, oh my God, okay. All right, now there's more people coming up, but oh well. There's important announcements that were made at the beginning of this. You'll probably want to go watch the video if you're just now checking in. The most important one being that the quiz for Wednesday is now going to be next Monday. It's going to be on probability. All right, let me stop sharing. Cool. So in the syllabus, I forgot that I did this. I said the quiz corrections are due the day of the next quiz. But I think I decided, I'm pretty sure I told all my classes that I decided to make the quiz corrections due the day of the final exam. You can definitely turn them in earlier, right? But I'll give you until the day of the final to turn those in, just like homework corrections. Okay? You can turn them in whenever you get done with them. That's fine too. All right. So any specific questions on homework stuff or other technical stuff or anything? There are some really funky problems that if I don't get questions on them, I get concerned, because that pretty basically tells me nobody's doing the homework because they are funky. So no questions. Okay. I'm always hopeful for you guys. All right. All right. I'm not seeing any questions. So we're going to get right back into where we left off. And that was working with probability. So I want to remind you guys what we got through last time. I want to finish up all the probability ideas, and then I want to try to do this worksheet with you guys. So this is not magnetic. Oh well, too bad. All right. So we've developed these so far. Do I need to adjust this? Let me pull up my, no, I guess it's all right. Yeah, you could probably go a little more. All right, and then, so we worked on this one. Yikes. I don't know if that sounds familiar to anybody. We developed this formula, and I want to point something out to you guys that students really don't understand, and I can't blame you that much. But do you remember how we did probability problems and then we figured out the formula? Remember that? We answered all kinds of probability questions without any formulas existing for us. And then we developed the formula based on what the hell we did. So if I give you a situation like a table or something where you can count everything you need, you don't need a formula. You don't. In fact, formulas make it harder. You never hear a math person say that. Will formulas always make it harder? No. If I don't give you a situation to count, where you can just count everything you need, then you have to use a formula. So let me give you an example of that before we go any further. So what if I said the probability of A is 0.2, the probability of A and B is 0.09, and the probability of A or B is what, Jeff? I don't know. Hopefully this works. Is 0.6. That should work. Yes. Can you figure out what the probability of B is? There's nothing to count. There's no table that I can go, oh yeah, there's 2 out of 8 people that said that. No, I mean, there's no table to use to construct fractions. Are you guys understanding? This is purely, they gave me values for these probability statements. That's all I got. So I need the formula to be able to do this. So how would you do this? What would you do? I see some of you guys writing away. Somebody's got to know. What do you do?
Subtract
Once you
from 0.9 and 0.6.
So yeah, you can just plug these in, right? Probability of A is 0.2, that goes there. Probability of A and B is 0.09, that goes there. Probability of A or B is 0.6, that goes there. So then I end up with 0.6 equals, right? 0.6 equals 0.2 plus, I don't know, minus 0.09. And then you solve it. Then it's algebra, isn't it? Oh shit, algebra has a purpose. Who knew? So at the same time that I say that formulas sometimes get in your way, I want you to realize they still have a purpose for existing. I'm not saying that all formulas suck. I'm definitely not saying that. Right? I'm just saying that for probabilities, the basic idea of probability is so basic. Is how many match what I'm looking for divided by the total. That's what it always is. That I don't need formulas all the time unless I got nothing to count, unless I can't make those ratios. Yeah, Sophia, you're right. I had to catch up with what you're saying. And then whatever the hell you get, I don't know. What do you get? 0.49? Is that what you guys got? Subtract 0.2, add 0.09. I'm pretty sure you get
0.49.
Kick ass. Okay. I like it. Did we develop any other formulas past this? I can't remember. I'm almost certain I must have done the given formula.
I don't remember if you gone over the formula for probability of A and B.
Yeah, and I haven't done yet. But I know I probably did given. Hopefully everybody has this. I'm erasing it. It's going away. Bye. We barely knew your problem. All right. So I'm almost certain we did probably A given B. Remember I told you that symbol means given? Yeah, I remember. We did this. Okay, thank God. So if you look at your notes, if you keep notes, then that should be in there. So, and again, we developed this formula based on what we did when it gave us the table of values. We actually did a problem before we knew what the formula was. So what I want to do is, so these are the two we know so far. We have one more formula to do, and that's what's the formula for and itself. And before I do that, I want to give a few examples about why it makes sense what it turns out to be. Okay, so any questions on what we just did? This is just a review of where we got last time. By the way, real quick, I might as well get this out of the way. Can you guys see my eyeball? Which eyeball is it? Yeah, you see how? Can you guys see how red it is? Yeah, so if I was in class with you, especially, so last January, I lost most of the sight in this eye. You don't want to know this, but I have to go every 7 weeks and get a shot. I get a shot in my eyeball. So every 7 weeks, my eye is going to look red. I'm going to scare people when I go to the store or something. Yeah, I know, Alex. It's basically as bad as it sounds. But if I was, I remember, so this happened last January, and when it first happened, people would come turn stuff into me, and I would be grabbing air because I had no depth perception. But now this eye is taken over, so I got depth perception. I haven't tried to play basketball. I tried to play basketball a while back, and it didn't go well because no depth perception is basically going to kill your game. But maybe I'll try now. Maybe this eye is strong enough to play basketball. We'll see. All right. Just in case you notice it's all red, so you don't. I wasn't in some fight, thankfully. So this, and now let's transition to this. So I have two examples about why the math makes sense on the given, on the and. Let's do the first one. Let's do the sad one first. Do you guys know the space shuttle? Do you guys remember the space shuttle? That program's been canned. I grew up in Florida for a while. What was it, from 6 to something? So when the space shuttle went up, we'd go out. We could actually see it. We'd go out to the street and we could see it take off. And the first time, I hate the fact that I have to say the first time that it blew up. I hate that I have to say that now, because of course it blew up a second time. First time it blew up, I was in school. For some reason, we didn't go watch it. And I remember I was in English class. I was sitting in the first row near the door, because I always did. Get the hell out of there quick. And the announcement came over, and I just started crying like crazy, because I was a big geek, still am, all about the space shuttle. Anyway, so does anyone know why that first shuttle blew up? Does anyone know why? Or you guys are aware it blew up twice, right? No, one time it blew up a few seconds after liftoff, and the next time it blew up coming back into, coming back from space, because enough of its heat shields had come off that it heated up too much and blew up across Texas and all that kind of stuff. They found parts of it all over the place. Now listen, stay with me. The first time it blew up, it's because they had in the gas line, they had what was called O-rings, which is a remarkably thing because they look like O's. It's crazy. That's awesome. And what they were basically valves so that it would flow, the gas would flow in one direction. It couldn't flow the other way. That sounds like an important thing, right? You want the gas to flow the right direction. So normally, now why do you think they had several of them in a row?
You need multiple burners.
Say again, sorry. Say again.
You need multiple burners.
Multiple burners. No. Why do you think in some neighborhoods you need like 4 or 5 locks on your door?
Protection.
Security.
So why one lock is protection, right? So why would you need 2, 3, 4?
Just like extra precaution.
Extra precaution, I like it. Or if there's a really important thing, you don't want to miss it, how many alarms would you set? Wouldn't you set more than one alarm? Yes, Jubal's got it. One could fail. So you do several. So if the probability that, let's make some shit up just to make them easier numbers, right? Let's say there's a 1% chance that this one will fail. And there's a 1% chance that that one will fail, right? What's the probability that they both fail? I can't add like an or because that goes against the whole idea. If I add, now it's a 2% chance the whole thing fails. That's dumb. Why would I put more in there then if the probability goes up? So I can't be adding things when I have an and. The probability this fails and that one fails. So what percent of the time does this one fail? 1%. Out of those times, what percent of the time does he fail? 1%. So it's 1% of 1%. So what's the probability they both fail?
1 out of 1,000.
So one out, not of 1,000, out of 10,000. So it's like 1 out of 100 times 1 out of 100 is 1 out of 10,000. Is that cool? Tens, hundreds, thousands, 10,000s. Now it makes sense. That's why you have multiple in a row. That's why you set multiple alarms. That's why you lock multiple locks. Because you're like, all right, if you can get through this kind, here's this kind, and this. If you're going to get in my house, I'm going to make you work for it. I'm going to make you earn that shit, right? Yes, maybe? No? Yes? Okay. So that's one thing. Maybe I'm not going to do this silly one. Yeah, maybe I won't do this one. That's fine. I think you guys get the idea. So whatever formula I get for and should have multiplication in it. And of course, now here's where I'm like, does anybody see how I can get a formula for and from what I've already got here? Mathematically, how would I get a formula for and?
A times B?
No, I can understand why you say that, but not quite.
Is it multiply B?
Yes. So I can multiply this up, so it becomes like that. So what the shit? There's multiplication. You guys with me? There's multiplication. But there's an adjustment made. Just like or is addition, but there's an adjustment made, right? Or is basically add. Why do I say basically? Because there's an adjustment made. And is basically multiply. Why do I say basically? Because there's an adjustment made. So what the shit is this? All right, now hold on. Stay with me. At least we see multiplication like we knew should happen from my space shuttle blowing up example, right? There's multiplication. So now we got to understand, why isn't it just like you said? Why isn't it this? All right, let's get into why it's not that. Okay. So let's see. I got to go back to this stupid thing, but too bad for everybody. Let's say we had 4 blue, 6 green. No, let's make it 6 red because 6 looks like a G already. 6 red and 8 green jelly beans. Let's not make it poker chips. Jelly beans. Right? And I reach in, and if I pick one, let's just start there real quick. What's the probability I pick a red jelly bean?
6 out of 18.
Yeah, 6 out of 18, 11. So 1/3, so about 33.33%. You can write that bigger. There. Right, that's cool, that's easy. What if I pick 2? Well, now I gotta be careful. Now I've got to identify something, and let's see if you guys see the difference. What if I pick 2 jelly beans with replacement? So I pick one, I'm like, I don't like that color. Let me pick another one, right? So I drop the first one back in, and then I reach in and pick another one. Are you guys with me? And then you're the next in line to get a jelly bean. You're like, putting your hands all over the jelly beans? What? So if I pick 2 with replacement. So this is this one. This is option 1. Here's option 2. What's the probability I get a red and then a blue? Okay. So this is not gonna help me explain this yet. So I'm still gonna have people like, what the shit? But too bad for me. I gotta do it this way. What's the probability the first one is red? Yeah, 6 out of 18. 33. The reason you don't use this is because it's rounded. I don't want to round to the end of a problem. So 6 out of 18 chance for a red, and means times. What's the probability I get a blue one now? So I put that one back in. So what's the probability I get a blue one?
4 out of 18.
4 out of 18. I love it. And then what's that going to be? 2 nines times 1/3 is 0.07. 0.07. I don't know. That's pretty close, I would think. Is it close? Somebody gonna help me out?
32 over 324.
What is it? Sorry.
32 over 324.
32. Well, it'd be 24.
Sorry, 24, yeah.
6 times 4, yeah. But what do you get when you do that?
1.333.
1.33.
Whoa. Okay. What? So it can't be bigger than 1. Are you guys understanding that? Are you doing 24 divided by 18? Is that what it is you're doing?
It's got to be 24 out of 324.
Yes, exactly. So I see. That's what some people did. 18 times 18 is not 18. So, I mean, if you do this, this is 24 divided by 18 squared, right?
Yes.
Don't be bringing no LCD shit in here. I don't need LCD. I happen to have an LCD. Math don't care. You multiply everything, right? Okay. And then whatever, you don't even need to do this shit. You just need to do this in the calculator, and you get what I said, yeah, 0.0741. So about a 7, almost a 7.5% chance. So not quite, Frida. Does everybody see that? Why that makes sense. And means multiply. So why is this here though? I'll show you. The fact that I put the jelly bean back in the bag, did anything change for the next probability? No. Everything stayed the same. I kind of like reset things when I put the jelly bean back in. I got red. I'm like, I don't want red. I want blue. And I put it back in, and then I reached around, and then I got a blue one, right? And there's a 7.41% chance that will happen. So what if I reach in and I do it without replacement? Meaning I reach in, I take one, I'm like, that's not the one I want, but still a jelly bean. And then I reach in again, right? And you're my little brother behind me. Jeff, be quiet. Yum, 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 yum. All right. So if I want to get the same thing, what's the probability to get a red one on the first pick? 6 out of 18. So that's and then I eat it. Yum, 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 yum. So then what happens then? If I've eaten it and I'm about to reach back in and try to get a blue one, what happens now? Sorry?
Is that a 17 now?
Yes, I think I can understand. It'll be out of 17 now, won't it?
Right.
And how many blue are still in there? There's still
4.
4 because I didn't need a blue. So this is the probability of red times the probability of blue given red. Do you guys understand that? Why is that different? Because it's the probability of blue given that I picked a red one. Because I'm doing it without replacement. Does everybody understand why there's a 17 there now?
Yes.
Okay, spokesperson has spoken. Because I ate one, so of course that changes. Why is that still a 4? Because what kind did I eat? A red one. And then what is that? I have no idea. It's going to be a little bigger than 7.4, probably 7.9. I don't know. I have no idea.
0.0784.
Well, that's pretty close. All right. Okay, I like it. Because, of course, the probability to get a blue goes up a little bit because there's less jelly beans. I ate one of them, so now it's a higher chance to get a blue one on the next go. So let's do one more problem like this without replacement. What's the probability I get a green and then another green? If I do it without replacement. So what I always do, then watch this. This is kind of nifty. I do like a little hangman game. I got 1, 2 takes. 1, 2 takes I'm going to do, right? So I make 2 little spots. What's the probability of the first dude? What's probably get a green? Nothing's happened yet. So what's probably
8 out of
going
18.
8 of 18. I love it. And then I eat it. Yum, yum. What's probably that I get another green now?
8 out of 17.
No. 7 out of 17. Is anybody out there going, why the shit didn't we change that one? We changed, well, because I ate a green one. So not only is there one less jelly bean, there's one less green jelly bean. So don't just change everything automatically. You got to think, I ate, but did I lose the same one I'm looking for second? No. So all 4 blue ones are still there, but now only 7 green ones are left. So if I had another, if I picked 3, the next one would be 6 out of 16, right? I would just make another spot and a green one and a green one and it's 6 out of 16, 5 out of 15, 4 out of 14, right? It would just keep going down, 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 down. And then whatever the hell that is, no idea.
0.1830.
Until I hear somebody yell differently, I'll go with that.
Yeah, that's right.
Okay. Let's try it. One more problem like this. I'm going to erase this top part here. Let me change colors up. Let's go with funky fuchsia. All right, let's do part D. If I pick 4 without replacement, what's the probability I get red, then green, then blue? So, I mean, here's how I would break it down for myself. How many spots do I need?
4.
4. They're connected by times because it's and. Red and green and blue. So probably the first one's the red one would be 6 out of 18. Right? What's probably the next one's a green one? What do you think the next one being a green one? What's the probability of that?
8 out of 16. 8 out of 8. 8 out of 17.
8 out of 17. I love it. So the bottom is just going to march right along. Do you guys see that? The bottom is just going to lose. Each time I pick a jelly bean, I'm going to lose one, aren't I? Can this ever change by more than one? No, because each spot represents one pick. I always have somebody that makes this go down by 6. I'm like, you didn't pick out all 6 red jelly beans. This is one pick, right? This is the probability that that one pick is red. Times 8 out of 17. And now what's the next screen will be?
7 out of 16.
Good, because I lost a green. And now how many blue are still in there?
4.
Because I haven't picked a blue yet. And then it's just whatever the shit that is. No idea. 1/2 of 7/15. 1/2 of 1/2.
Point.
Oh man, I almost got it. 0.01.
0183.
0183. All right, that was pretty close, right? Okay, it's my one skill. I got to show off every now and again. And you're all like, that's a really boring skill, man. You're not going to make much money from that. All right, well, shit. I'm not going to take this on the road. Don't worry. I don't know how you guys feel about that, but remember, and is multiply. Why does that make sense? Do you guys remember the bouncers, the story about the bouncers? No? You guys have forgotten about the bouncers already? The and bouncer is nice. Remember, I mean, is mean, and the or bouncer is nice. So if you have an and bouncer, less people get in because you have to meet all the requirements. So when I multiply two numbers that are less than 1, what happens to the result? It gets even smaller. So the fact that I multiply when I have an and goes along with the basic idea that and always makes things less and less and less because it's harder to match all the requirements. Or is addition. That's going to make it more. Right? Or is nice. More people get in. And is mean. Less people get in. It goes right along with the math. So what does or basically mean?
Addition.
Addition. And what does and basically mean?
Multiply.
Kick ass. If you just remember that, no, I want you to remember everything. But if you absolutely can only remember one thing, that's the thing. I guess it's technically two things, but I'll get over it. Okay. So I think, I'm trying to remember if I forgot anything. There's a couple things real quick. Yes, there are a couple of important things. Do you guys know how many cards there are in a deck of cards?
52.
Does anyone not know that before he said that? Is anyone like completely bad with cards? I'm not going to say you have to suddenly know how to play Texas Hold'em. I'm just saying, do you know how many cards? 52 cards. Do you know how many suits? Like if I started it off, 4 suits: hearts, diamonds, clubs,
and spades,
clovers, balloons. No, that's Lucky Charms. Sorry. Okay. So what's the probability if I reach into a deck? What's probably get a king if I just reach into a normal deck of cards?
4 out of 52.
4 kings out of 52 cards. I love it. Isn't that 1 out of 13? Which is, I have no idea. If somebody can help me out.
0.0769.
Thank you. Sounds about right. Now, what's the probability I get a king given it's a club? So given that it's a club, How many clubs are there? There's 52 cards, 4 suits. So there's 13 cards in each suit. So I just told you directly. If I know it's a club, that makes the bottom out of 13 clubs. And out of those 13 clubs, how many are kings? 1. There's 1 king of clubs. Careful, not 4. It's got to be a club. Is that the same as what it was before? Are these the same?
Yes.
Yes. I love it. You guys, I love you guys. You're all like, there's a trick. There's a trick. No, they're the same. It's freaking the same. What can I say about that? So what does that mean, Jeff? What does that freaking mean, Jeff? It means that, let me see if you guys get this idea. What word would I use to describe these two events then? I would call them independent. Because knowing that I have a club, did knowing that change the probability it's a king? Did knowing this change the probability of this?
No, it didn't.
No. So wouldn't you say that they're independent? One doesn't give a shit about the other one. Maybe?
Yeah.
But watch this. So these are independent. King and club are independent. What's the probability to get a king given it's a face card? All right, this could get kind of weird. I'm really sorry if you don't know cards too well. But how many cards have a face on them? The king?
There's 3.
That's
King,
right.
queen,
the king,
and the jack.
The jack. And there's 4 suits. So how many total face cards are there?
12.
12. So out of those 12, how many are kings?
4.
All 4. Right? I didn't throw any kings out. Here I threw out the king of hearts, the king of spades, the king of diamonds. So that's 1/3. Did that change? Did that probability change?
Yes.
Yes, that probability changed.
That probably went crazy. It went from 7.69% up to 33%, right? That probability changed a lot. So are king and face card, are they independent?
No.
Yes.
No, because knowing this changed the probability. Probability is a king changes if I know it's a face card. Knowing this changes that. So let me ask you this. We live with this. We used to live this a lot. Remember the times, remember the before times, before the pandemic, and we could drive. And if you look at your watch, let's say you're up in North County and you live in La Mesa or something, and you look at your watch and it's 4 o'clock, right? Am I thinking about the right direction? I think I'm better this way. Let's say you gotta screw it. Certain times a day, you do not want to go in certain directions on the road, at least before the pandemic, right? Now it's basically, who knows? I don't know what it's like out there. You guys semi with me? So we go, given that it's 4, the probability that I'll get home anytime soon is really low. So I might as well just stay where I am, get another drink. Maybe not. Maybe some food. I don't know. Are you guys with me? Anybody have that happen? Where I go, guys, we got to leave like now if we want to hit that magic window before everything goes to shit on the roads, right? I'm almost certain you must have lived that experience. That is a given. Given that is this time, I don't want to hit the road now. We might as well stay for a while, right? Basically from about 3:30 to 6:30 roughly is shit on the roads. Okay, all right. So that's an example of this. Given that it's this time, what's the probability to get home soon? Not good. It goes way down. So screw that, right? So what I'm saying is this. Here's the shortcut of what I'm saying. If I ask you, if you get a question about A and B, are they independent? You have to check if the probability of A given B equals the probability of A. Then they're independent. Otherwise, dependent. So if B happens, I really want you guys to be able to see this. Everybody has trouble with this. and it drives me a little crazy. It really is nothing more than this. If B happens and the probability of A doesn't change, the probability of A given B is the same as what the probability of A was before, then they don't give a shit about each other. They're independent. If this is different, that means that B happening changes A, and that's dependent. This is one place where math people actually pick the right words. Independent and dependent make complete sense here if you let them. Okay. I'll let you chew
I
on
have
that
a
for a second.
question.
Go ahead. I'm going to turn my AC on.
Could you maybe use numbers to show that? Because, I mean, it makes sense what you said, but could you use numbers to show how it could be independent or dependent?
Yeah, let me summarize what we just did. Because the whole thing with the king was me doing exactly that. So the probability of a king was 1 out of 13. The probability of a king given club was still 1 out of 13. So these are independent. But the probability of a king given face card was 1/3. So these are dependent. The probability of a king is this. Did this change it? No. Did this change it? Yes. So king
Got it.
and club are independent, whereas king and face card are dependent. Bah. You're telling me that's the word dependent.
I have a question. Does with or without replacement affect dependent?
I love it.
Dependent?
Now you can think back. If I do something without replacement, do the probabilities change? Yes. Therefore, without replacement is an example of dependent. With replacement, everything stays the same, right? So that would be independent. I love it. So now, I love it. Sophia, tell everybody, I did not plant you to, I'm just joking. It's almost the perfect question for this. All right. You guys have what you want from this? Remember this formula? You can do it, Jeff. What was it? I've already forgotten. There it is. This is basically the formula. But if A and B are independent, what is this? If A and B are independent, what is this?
Dependent?
What? Sorry?
Dependent?
But what is it? Does the probability, does A affect B if they're independent? No. So this would still be the same thing as that. And look, that does exactly what you wanted it to, doesn't it? Right? Remember, you at first said it should be probability of A times probability of B, and I showed you why that's wrong, because that's the more generally correct one. What's the only time it's this is if they're independent. And that, going back to the Challenger real quick, that's the mistake they made, was the day it was icy. It was icy that morning. And that affected all of the O-rings. They all decreased in their reliability. So the probability that they would fail went up, all of them. So it wasn't independent anymore because they were all affected by the ice. And that's why it ended up blowing up. It should not have blown up, except they were icy. They weren't able to do their job as well. The gas went the wrong way, and then it happened. Okay, maybe. Okay. But I think it's going to help.
A question.
Yes.
Could A be dependent on B, but B be independent on
No.
A? No? Okay.
No. If the probability, so here, if I did this face card given king, it would also be different from face card. if one affects the other one, then the other one affects the one. It goes both ways.
Okay, gotcha.
Cool. And we all do this. We all do this kind of thing. Shit. I can't think of anything except the traffic thing. Anyway, screw it. All right, one more thing to show you. The formula for OR is this. What if this was true? Jeff, you need a whole separate word. I know. If this is true, how does this change? Like that, right? So, and this would mean that nothing in A is also in B and vice versa. The word we use for that, the phrase we use for that is mutually exclusive. They mutually exclude each other, right? So one says, I don't want you in my club, and the other one says, well, we don't want you in our club. So they mutually exclude each other. So an example I used to use is dog and cat, and then that crazy ass cartoon came out, Cat Dog. I don't know if you guys remember that cartoon. And now I use rock and ice cream. Can you be a rock and ice cream at the same time? I don't give a shit if you can make ice cream look like it's a rock. Is it a rock? No. So rock and ice cream are mutually exclusive. So really, look at that. That one says that A or B equals A plus B. That one, if this is true, the equation is so much simpler. Of course it is, because there's less going on. Okay. So I desperately need you. Let's take like a, do you guys want to take a little break? What time is it? It's 2:17. We could take like a 10-minute break. What do you think? Before we do work with this? Yeah, let's take a 10-minute break. And if you have questions you want to ask, you can ask away. Or you can just sit there and stare at me. Hopefully, you can take a little break. You can go grab a drink. You can, take your favorite.
I have a
whatever
question.
Yes.
So it's in regards with what Sophia had said earlier. So with is independent and then without dependent.
Yeah, with replacement means you reset things. So that is independent, beautiful.
Okay.
And without replacement means things change. So that would be dependent. Because if I pick a jelly bean out and I eat it, the probability I get something depends on what jelly bean I just got, right?
Mm-hmm.
Given that I got a green one, the green one's probability definitely changes. But all of them will change because there's one less jelly bean. So if I don't put it back in, if I do it without replacement, that's a dependent situation.
Okay.
Because it depends on what I picked. But when I put it back in, that kind of resets everything. Then it doesn't matter. It doesn't matter what you picked because they're all back. I like it.
Thank you.
You're welcome. All right. Maybe I'll pause this. Thank you. So let me share this. If you're on Canvas, or you can get on Canvas, do so now. Let me see. Because if you go down, there is now a Unit 3 module. Is everybody back? Hello? If you're in the other room, come back. Hello? Okay. Here come people. All right. So if you go to Canvas, log in. Here's the Unit 3. There's a probability worksheet right here. What I want you to do, let's do this a piece at a time maybe. So on this side, see how it says this side in class? So, we're technically in class. And the other side is something you can do yourself, and I'm going to have an answer key posted on Wednesday. So this side is kind of like a practice quiz. That's a little bit of a preview for Monday's quiz. You with me? So we're not going to do this one today. That's something for you to do on your own time. But I want to do this side today. Get up there. So let's try to do number one. Number one is a nice review of what we did last time. So try to do number one. Let me share it a little better way. So go to Canvas. It's under the, what do you call it? Don't worry, I'm going to open this up again. It's under Unit 3. It's crazy. And let me share this in a better form. Hold on. Where's my better form? This is my final form. Where? There you are. Okay, let me share this. Share. Get over there. I think that's the right one. Yes. There you go. You see it now? Okay. So try to do number one. Let me make her stop now. Where is she? How can I do that now? Over here. By the way, so rude. I always forget. I don't think I showed this class. I can't remember which classes I've shown this, but when you go into breakout rooms, do you guys know about that green button at the bottom of the screen? It says share screen. So anytime I hit breakout rooms, you can hit that button and there's like a whiteboard you can share and everybody can write on it. Or even if somebody's a little more savvy, they can share the document you're working on and you can all write on that. So it's up to you. I mean, if that would help, you've got that ability when you're in a breakout room. You can do that. So let me see. Let me share this thing. Okay. So obviously, the first place you start off with this kind of problem is to fill in. This is why I'm kind of nice. And oh no, I'm going to have to do this over. Sorry. Stop share. Move this over there. Move you guys over here. Move this up. Share my screen. Share that one. Over there. Okay, now. So if you add these up, so kind of help me out as I go. I'm just going to do this on the fly. We'll do it live. Oh, shit. What's that going to be? 126? Is that right?
Yeah, 126.
50. So then you got 176 total. Kick ass. Sweet. So that's the first thing you do. Now you can answer any probability questions. You don't need any probability formulas besides the most basic one. So a 10's Grossmont, you just need how many match that out of total, right? And of course, how many match the 10's Grossmont?
126.
26. Good. So when you do that, what'd you guys get?
0.7159.
I like it. I can't remember. Did I say it on this sheet? No. Did I say it on this sheet? No. Here it is. Yeah. I normally say this. Same thing I said when we got into this stuff. Round decimal answers to 4 places. Okay, I like it. So that is that one. And then they just keep going. So I'm gonna kind of, if you get part A, the only other thing that people make a mistake on is these don't build on each other, right? This is its own problem. So you kind of start over, 176 people, 92 business majors. So then whatever the hell that is.
0.5227.
Yeah. And if you want to, you can certainly make them into percentages. That's fine too. Either way. Because I've heard humans like percentages better. You humans. I am a human. So is a computer science major or attends Grossmont. So the one thing you gotta be careful about here, if I count all the computer science majors, there's 73 of them. The Grossmont students, there's 126 of them. What mistake have I made?
You have to subtract 62.
Yeah, I counted these people twice. So I would have to subtract 16. Now, you could be smart about it And you could say 126 Grossmont students plus 11 I haven't counted yet. That would be fine. That's being smart. Because here, what's 73 minus 62? 11. That's the 111. So then you get 137 out of 176. And whatever the hell that is. Oh,
0.7784.
Yeah, buddy. I like it. Coolness. Now, here's the first place where people desperately try to bring formulas in, and it just goes to shit. The formulas will work. They will be disgusting. They would be disgusting. This is so much easier. How many people do this and this? Somebody else. I know Janik knows. I know more people got this answer.
Two.
Yeah, there's only 2 people that are Cuyamaca students and they're math majors. They have to be both. There's only 2 that do both out of
76.
176. The bottom doesn't change because I didn't give you any information. And then, you know, whatever the hell that is. There we go. 0114, it looks like. Let me stop for a minute. This kind of problem, you just got to eat it up. You just got to go, yes, Jeff, thank you. And you make all the ratios. If you got this as an answer for something, if you got like 185 out of 176, what do you think? If that was one of your answers to one of these questions, what do you think this would mean? Is this an okay answer?
No.
No.
What is wrong with this answer? I don't even care what the question was. How do I know that answer is wrong?
It's more than 100%.
More than 100 freaking percent the shit. I mean, so if the probability is going to rain tomorrow is 110%, what does that mean? Does that mean the raindrops are like this big? So don't go, boom, oh my God, you get concussion just by walking. Does it mean it's going to rain so hard it's going to rain in the next universe over? What the shit does that mean? It doesn't mean shit. So please, if you get something more than 1 or more than 100%, don't just circle that shit. If you don't see what you did wrong, do this. Not sure what I did wrong, but I know it shouldn't be more than 1. Do something. And I will give you a point for that, for at least knowing it shouldn't be. But if you just give it to me like that, you're losing all the points. That is a very basic idea of probability. They cannot be bigger than 100%. So be very careful. Pay attention. Don't just do the math and get lost in numbers. They have to mean something. So this is the only one where the bottom changes. What does the bottom become?
$73.
Yeah, because I know they're computer science major. There's 73 of them. And out of them, how many go to Grossmont?
62.
62. I like it. And then whatever the hell that is. I don't know.
.8493.
Yeah, 0.8493. I like it. So then this question, are being a Grossmont student and a computer science major independent? Well, you look at the probability of Grossmont versus the probability of Grossmont given computer science, because I did that work. The probability they go to Grossmont is 0.7159. The probability they go to Grossmont, given that if I know they're a computer science major, does it change? Yeah, it goes up. So those are not equal to each other. Knowing they're a computer science major changes the probability they're a Grossmont student. So therefore, what's the answer?
Dependent.
I think you're saying
they
this.
are dependent.
Dependent. I like it. Because what's the probability they're a Grossmont student? Well, it depends on if they're a computer science major or not. Right? Doesn't it? Because it changes. If I know they're a computer science major, it changes. Maybe.
To clearly answer why or why not, it would be no,
Well-
because the probability changes.
Yeah, this is the why or why not. All this work right here is the why or why not. And that's just to cover myself. If somebody says no, I don't have to give them the points because of this question, right? So this is the why or why not. But yeah, if you wanted to go further and say in words, it changes the probability, I'm cool with that too. Is anybody not with me? Okay. So I think at least a few groups got into number 2, and number 2 should be relatively simple. Let's see what time it is. Okay, here, we'll stop very soon, all right? I like this idea, though. This is kind of nice. Just lock them all up in a freaking haunted house. Let Pennywise chase after them or whatever, right? If I pick somebody at random, what's the probability the person's a Democrat? This should be pretty straightforward.
7 out of 21.
Good. You got to know how many total people there are. And out of that, there's 7 Democrats. So that'll be that bad boy, right? What about Republican?
12
12 out of 21.
I like it. 12 out of 21. And then whatever the hell that is. 4.7. So like 0.57?
0.5714.
0.5714.
Kick ass. All right. Everybody cool with that? I kind of gave it in 2 different ways. I don't care. You can make this into a percentage if you want to. I don't care. It's all good. They're the same number. Now we're doing with replacement. And I'm going to select 2 people. So I got 1 empty spot times another empty spot. So the first one is independent. What's the probability the first dude is independent or dudette?
2 out of 21.
Good. And then I put this, so I take them out and they're like, oh, thank you. And then I throw them back in and I laugh a little bit. And then this is kind of a cathartic problem, I thought. And then what's probably then I pick another one that's Republican.
12 out of 21.
Yeah, nothing changes, right? Because it's with replacement. So then, you know, whatever the hell that is. I don't know. It's like 0.05.
0.0544.
All right. Is everybody with me? So with replacement, I put the first thing back in. And then the second thing and the third thing, however many picks. So none of the probabilities change from spot to spot. So 2 Democrats. The first one's a Democrat, then I throw them back in. So the second one has the exact same chance. And that, just to show off, will be 0.111111. I like it. All right. Now, things get a little more interesting. And what I like to do is I like to ask the exact same question, but since it's without replacement, the first one's still 2 out of 21 for independent, but now what's the probability it's a Republican?
12 out of 20.
Yeah, I lost a person, but I didn't lose a Republican, so that's still 12. And that's like 0.059?
0.0571.
And then this one, same idea, but now it's 2 Democrats, right? So it'll be the first one is still 7 out of 21. Man, 7. Rein it in there, buddy. Go away. And I let them leave. And then I reach in, I pick another Democrat. What's that going to be?
6 out of 20.
Good. There's 1 less Democrat, 1 less person. And that's going to be 10%. So if I, right? Yes. Cool.
All right.
Woo! So I'll tell you what, we'll do, well, let's see. Let's finish this one up real quick. What time is it? Yeah. This one's a very interesting problem. I talk about chocolate milk. I talk about, what is it? Brussels sprouts. Did you guys hear about this? This was an actual survey Now, the language on the survey was a little misleading, but still, the fact that 7% of people effectively picked that chocolate milk comes from brown cows, that, to me, that explains a little bit about where we are currently in this country. But don't go that way, Jeff. Don't go there. Don't go there, Jeff.
Higher.
That's bad. Sorry, say it again. You're surprised it's not higher?
Yeah, I'm surprised.
I understand.
It's not higher.
I understand. But real quick, if I select 4 Americans, just like up here, I was selecting 2 Democrats. There's now going to be 1, 2, 3, 4 spots, right? The difference is, how big was the population in number 2? There was only 21 total, right? Right? How big is the population in number 3? Don't say 4. How big is the population in number 3?
All Americans?
Yeah, which is roughly 340 million.
350, 340, something like that.
Something like that, yeah. So, what I can do, look what I can do. What's the probability that the first one thinks that chocolate milk comes from brown cows? That's a 7% chance, right? What I can do when the population is so large, I don't have to make fractions and make the numbers go down by 1 because the numbers are so freaking big. If I take 1 away from 340 million and make the bottom become that, it's not going to change things. Not maybe in the 15th decimal place. So I'm allowed to do this. What's the probability that the next one doesn't believe this?
0.93.
Yes. And then the next one, and then the next one. So let me show you something kind of cool. You could throw all that shit in your calculator, but notice I can also write it like this. Do you see? And if I put a 1 here that we normally don't, see how I got 1 of these and 3 of these?
Question.
Yes.
How did you get 0.93?
Well, if 7% think this way, what percentage don't think this way?
93.
Oh, okay. I get you.
Cool. I like it. I like it. Beautiful. And then whatever the hell that is. So we'll finish up the other 2 next time. Maybe go ahead and take a look at them, see if you can do them. They get a little bit freaky. But that is basically the same idea as number 2. It's just that my population is so big, I don't have to use fractions. Can you imagine? You'd have to put 7% of 340 million over 340 million and then take it down by 1. Screw that shit. The numbers don't change enough to worry about that. So we'll finish up number 3 next time. I'll let that stay there for you to think about. All right. Otherwise, class is over. So if you have questions, please stay and ask your questions. Otherwise, you can leave. Go rewatch it. Chapter 1 and 2.
So the answer for 3A would have been 363.049.
Whoa, wait a minute.
I'm not sure if I'm doing that correctly.
0.07 times 0.93 to the third.
Yeah.
So I get 0.0563. Of course, I get something very tiny because you're multiplying tiny numbers times other tiny numbers. That should come out to be really, really tiny. So I'm not sure how you're putting it. Let me see if I can do this. Hold on.
Oh, I see what I did wrong. I put 0.7 instead of 0.07. Okay. I can barely see it.
I know. Hold on. I'm trying to focus it. There we go.
Oh, I see now.
0.07 times 0.93 to the third. Yeah.
Okay.
Now I'm all blurry. Okay. How's everybody else? You guys all right?
I had a question about F and number 1. So we know that the answer is no, But if somebody did the work wrong and still got no, would that count as half credit?
If you had the right idea of what to check, then I would give you most of the credit. What did you do wrong?
I got like mixed up on what numbers to use to figure out the computers. Like computer science major, I used the wrong numbers. That's all.
Did you use 73 out of 176? No.
Yeah, I did like
Oh,
73 out of 176, and then I did 63 out. It was a lot. It was very wrong.
but here's the problem. That one is going to lose a lot of points because there is no reason that the probability of one thing should ever equal the probability of something else entirely. The point of part F, the only probability thing that we do that shows how two things interact with each other is the given. And if you don't do anything with how they interact with each other, you cannot answer part F. It's all about how they interact. One thing's probability by itself and another thing's probability by itself. How does that show me how they affect each other?
Oh.
So you're never going to compare two completely separate probabilities. There's no reason that they would be equal. You want to compare one to the interaction of the two, which is the given. That's why you got to do the given.
Okay, that makes sense. That was
I like it. Yeah, good question. How's everybody else? You guys all right? All right, I'm going to head out. I don't see any other questions, so I'm going to see you guys later. Bye.